Example 223, slide 17. Last time, I have talked about the sizing of reactors. So sizing a CSTR or sizing a PFR, we have not finished in example 223, right? So we have finished A and B, right? A and B, we have not finished C. So let's see the question. Finally, make a qualitative sketch of the conversion and the rate of reaction down the length or volume of the reactor. So what is the meaning for this question? Qualitative means you don't have to write down all the data. You don't have to get all the data. Maybe 3 or 4 or 5 points, you can have a qualitative sketch. And this sketch is for conversion. For conversion, X, rate of reaction. What is the meaning? Down the length or the volume of reactor. That means you have to plot two figures. One is conversion versus volume. The other one is reaction rate versus volume. Okay, conversion and the rate of reaction down the length of reactor. So that means A. That means let me see. Sorry. Down the length of reactor. The XY axis is inverse. Down the length of reactor, that means conversion change with volume. So X axis is volume. Sorry. X axis is volume, and the Y axis is conversion and the reaction rate. Okay, so let's plot these two figures. So to have a curve, at least I think you need 3 points, right? The more the better, but at least you need 3. Because 1 point you cannot get a curve. 2 points you only have a straight line. But if you have 3 curves, maybe you can have a similar curve as a result. So at least 3 points, but the more the better. So let's see how many points you can obtain to draw this line. So for here, let's use a 3-point method. Okay, last time I have told you about maybe at slide 18. Slide 18, I told you about a 5-point quadrature formula, right? To have a approximate curve. So now we can use just 3 points to do the integral. But the 3 points method is weaker than 5 points. So let me introduce you first about the 3-point method. Okay. It is similar to the 5-point method. So you have integral from x0 to x2, right? Because we are only 3 points. your target is like this. And then you have okay. H is equal to this one. That is the 3-point method. By using this one, we can get a more integral. We can get a more value to draw the line. Let's compare. So you can memorize these two together. You can compare this one with the 5-point method. We have mentioned, right? You can compare. So for the 5-point method, let me put a different part directly in this equation, okay? So for 5-point method, this part become x4, right? And here, the coefficient is 1, 4, 2, 4, 1. 1, 4, 2, 4, 1. So 1, 4, 2, 4, 1. Okay, for 5-point method. How about H? H will become x4 minus x0 divided by 4. So these two methods can be used to integral, for integral. This one, the answer obtained using 5-point method is closer to the real value, right? Because there are more points. But this one is much easier because you only use 3 points. But the answer is less close to the real value. But if you just want to have a qualitative curve, not a very accurate, you can use the 3-point method. Okay, so let's see how many points we can obtain to draw the curve. You can see the table, the data in the table, right? So you have conversion equal to 1, 2, 3, 4, 5, 6, 7. 7 points, right? And you have the data versus this value. If you want to use 3 points, what is the data you can use? The first set is you can use these 3, right? The gap between them is similar. So first you can use these 3 data and find the volume when conversion is equal to 0.2. Okay? When conversion is equal to 0.2, you can use these 3. Use this 3-point method to get a value necessary for the conversion equal to 0.2. So what's more? We can have another choice. You can have 0, 0.2, and 0.4 to obtain the volume at conversion equal to 0.4. Okay? So there are 2 additional value for you. We already have this one, right? the volume for conversion equal to 0.8. We have calculated at A, right, the question in A. We use 5-point method to find the value. Okay, so let's find these two volume. Okay, using the 3-point method. Any question? If not, let's continue. First, find the value conversion equal to 0.2, okay? So the integral is from 0 to 0.2. F of x is equal to fa0 over the rate constant dx. Right, I just write down this part. Then h over 3. What is h? 0.1, right? If you cannot tell. 0, 0.2. This gap is 0.1. Okay, continue. What is F0? F0 means the least value at x equal to 0, right? So check the table. Check the table. The data is from the table. So this value is 0.89. 4 times F1. So F1 is for x equal to 0.1, right? So you check from the table, 1.08. Last one is the least value at conversion equal to 0.2. Okay, so calculate. You obtain this one. Can you calculate V at conversion equal to 0.4 by yourself? I give you 3 minutes, okay? After 3 minutes, I will tell you I will give you the answer. So please use the 3-point method to calculate this one. Let me give you the answer first, and I will give you the formula. So you can check if your answer is correct or not. So please calculate it now. After 3 minutes, I will tell you. Okay. So we got a 3 point. So let's put this point in one table. So you got x equal to 0. Actually, you don't have to calculate this point, but you have this point. Conversion equal to 0. At the beginning, right, you have conversion equal to 0.2, 0.4, also 0.8. Okay. Try to use a table to make the data to be easier to read or understand. What is minus RA? What is reaction rate? Please calculate reaction rate from the table. Okay, you have FA0, right? FA0, the molar flow rate of A is equal to 0.4. So you have FA0, you have FA0 over minus RA, so you can calculate. You can calculate this one. Let me put a unit. Yeah. Mole over cubic meter per second. The volume we can use, okay, cubic meter. Okay, so let me write down. So this row is from table, okay? From table. The question should give you the data, but you should calculate the value. So conversion equal to 0 means at the beginning, right? At the beginning, so volume is equal to 0, okay? At the beginning. 0.2, we just calculate. 0.4. And a 0.8. Okay? Try to use this data to draw a curve. So the first curve is volume conversion. Okay, so you have conversion 0, 0.2, 0.4, and 0.8. 0, right? M could be 1, 2, 1.5, 0.5. You can roughly put a data, but 0 should be accurately drawn here, right? 0 is very obvious, so put a 0 here, 0, and then 0.2, so maybe around here, and 0.5, 0.4. Okay, the 2 point something, 2 point something. Okay, so you can get a curve like this. If you give me the curve like this is wrong, okay? The trade should be the same. So this point can be not very accurate, but the trade should be the same. So this curve is wrong, this curve is correct. And also this point is important. How about another figure? Another figure is for volume versus reaction rate. Reaction rate, right? Okay, so you see these two. The value is very small. Value is very small. Let's have the value for x-axis. So so 45, 30, 20, and 5. Okay. Okay, so the top one is 0.45. I have 9 gaps. Okay, so for each one is 0.05. So 5, 10, 15. 20, 25. So the 30.3 here. 0.2 is close. Okay. So draw the line. 0. 0 and 0.45. Then this one. This one. And the last one. Okay? So you got a curve, maybe like this. The trade is important. So again, if you give me the curve, if you give me the curve like this shape, it is wrong. So make sure you put the accurate point of 0, 0, accurate point of 0.45. Okay, because this value can be roughly pointed, but this value is very obvious. You should give me the correct point. And also for the axis, you should give me the target, right? What is the target for you in x and the y axis? And remember the unit. If you give me the curve like this, it is not accurate. Maybe I will give you half of the score. You should give me 0, right? 0. Original point is important. Also, you should give me the unit. And at least have some point for me, okay? The blue one is not very complete. Put the information, all the information. Okay. Any question? I suggest you to have this table first. It is better for you to draw the curve. Just collect all the data for yourself. It is easier for you to have data, right? And the data. Let's go to the next example. Slide 24. Example 224, comparing CSTR and the PFR sizes. Hello. Comparing CSTR and the PFR sizes for the same job. So this example is the conclusion for previous two examples, right? Example 222 at slide 14 is to size a CSTR. And the example at slide 17 is to size a PFR. So let's compare the size for CSTR and the PFR for the same job. So again, using the data in previous two examples, the conversion is 80%. So calculate the volume for CSTR and the PFR. The entering molar flow rate is also the same, right? 0.4 mole per second. And the feed conditions are the same. So everything is the same. So I will not calculate again. Let's just compare. So from the previous two examples, you know the volume for CSTR is equal to 6.4. The volume for PFR is equal to this one. Okay, so this is the first conclusion. But for you, when you take an exam, you have to calculate, right? You have to calculate for me. So the conclusion is PFR require smaller volume. Also, another method, you can just have a plot. You can just have a plot. So remember what is the plot. You should write down the original point, okay? And what is for x-axis conversion. What is for y? FA0 over minus RA, the reaction rate, and the unit. Okay? So this is the standard form of a figure. Next, you may have a curve. This curve is from the example, okay, from the problem. The problem will give you a table, right? You can draw a curve from the table, and then for the conversion equal to 0.8, you can show me this one is the volume of PFR. Okay, so this one. The rectangle one, you have volume of CSTR. So from the conclusion, from the area, we know the area for PFR is smaller than the volume for CSTR. So you can use two methods to give me the conclusion. So please remember, if you want to find the value for reactor, you must have to put a conversion here, put this term here, okay? If y is not this one, x is not this one, the integral area is not value. Okay, x versus fa0 over minus IA. That kind of curve can give you the value. So let's go to the next topic. Reactors in series. So usually reactors are connected in series. So usually not a single one, okay? We don't use the single one reactor. We'll do the connection in series. So how to calculate the conversion X in series system? So first, we define the conversion. Please go to slide 25. 25, okay? Reactors are connected in series so that the outflow of one reactor is the inflow for another reactor, right? Because they are connected in series. So let's define the conversion XI. I means the number of reactor, the sequence of reactor. So Xi is equal to total mass of A reacted up to point I. What is point I? Point I is the point after passing reactor I. So after passing the first reactor, reactor 1, you will arrive point I. I will give you a picture. You can know better. So pay attention to the first. Xi is the conversion versus mass of A into the first reactor. Give me one minute, okay? So maybe you have 3 reactors connected in series. The conversion here is related to FA0, okay? The conversion here, you should calculate with the mass of A fed to the first reactor. So there is no relation with the second one. Second one is the previous one, right? So you cannot consider this one as a single one. If you consider this one as a single one, maybe you will check here and here, right? Inflow, outflow, and calculate the conversion. But in the series system, we only consider this point and the beginning, the point at the beginning. Do not consider the previous one. So remember the definition. Let's take a rest. Hi. Let's continue. I think you have two sentences or one sentence at the bottom of slide 25. Right, I think you have this one printed out in your handout. This definition is used when the feed string only enters the first reactor in the series, and no side string fade or withdrawn. 这个定义只有用在你的进料只从第一个反应器进去。如果你在第二个、第三个也进了一些东西，就不能这样算，就会更复杂。所以现在讲的 the first example for connection in series, we talked about the simplest case. Okay, the simplest case, so the feed is just from first reactor, so no side string. So go to the second slide 26. So there is a figure, right? Let me draw this figure. So the first reactor, the volume, we divide it as V1. In flow, molar flow rate, FA0. Okay, so after, when the string out of the first reactor, this point, we have a molar flow rate, FA1. So after first reactor, you got a FA1 and X1. Okay, the definition is like this. So the feed is defined as 0, FA0. So after reacting in the first reactor, you got a 1, FA1 and X1. So similarly, go to the second reactor. The volume is V2. So after second reactor, you got a FA2. This point, FA2, and the conversion is X2. So continue. Go to the last reactor. So volume is V3. After this reactor, you got a FA3 and X3. Okay? So remember the definition for conversion is to versus the feed to the first reactor. So how to calculate the conversion? CSTR in series. CSTR in series. Slide 27. Next one. So consider the simplest case. They are two, right? The simplest one, two CSTR in series. So the picture is like this. This is the first CSTR. Second CSTR. The feed string, FA0. Molar flow rate. The reaction rate in the first reactor is minus RA1. Okay, RA1. After reaction, at this point, you get a FA1 and X1. Okay, so go to the second reactor. The reaction rate is minus RA2. So out of the second reactor, you got a FA2 and X2. Okay. This is the simplest case two CSTR in series. Now I want to derive a formula for the volume. Okay, so let's begin from the more balanced equation. As I told you have to go to the very beginning to derive the formula or equation. So more balance. Let's have more balance on reactor 1. Okay, on the first reactor. More balance on reactor 1. You can write down at this slide 27. So the more balance is like in minus out plus generation or assumption. Consumption is equal to 0. If you forgot, please check chapter 1. The flow reactor is in steady state. So this term is equal to 0. So you put the symbol, okay, what is in? Just consider this one, okay, consider this one. Inflow is FA0, right? Outflow, FA1. Generation, RA1 times V1. Very easy. We need another equation. Okay, we need another equation. So just consider one thing. For this equation, which term, 1, 2, 3, which term is harder to obtain? 哪一项最难得到? This one is initial, right? At the beginning, the molar flow rate. So the question should give you the initial condition. This is initial condition. Also, this one is from the problem. We want to derive this one. Okay, so now I want to use another equation to replace FA1. FA1 is the molar flow rate in the middle of the series CSTR. So this is maybe harder to obtain. So let me use another equation relating to conversion. So FA1 let me find where you can find this one. We have talked about this one. At slide 9, okay? If you forget, please, you can go to slide 9. We have talked about a more balance relating to conversion. So it is FA in slide 9. We have a formula in slide 9. FA is equal to FA0 minus FA0x. But now, it is serious, right? So we put a 1 here. We just put a 1 here to represent the reaction after reactor 1. So combine these two. Please combine these two. We obtain the volume of first reactor. You don't have to memorize that formula. You just memorize the more balanced equation. And maybe you should memorize the equation for conversion, then combine. Try to combine. It is easy. It is simple calculation. But you can still have some impression for this one. Depend on you. For the second one, wait for 1 minute. Next, I will talk about the volume for second reactor. You can write down at slide 28. Next slide. For the second reactor, reaction rate of A is minus RA2, okay? The conversion is X2. So similarly, let me do the same thing. So the more balance on reactor 2. More balance on reactor 2. The more balance should be the same. It is definition. So in minus out plus generation is equal to 0. Put a symbol, right? So now you consider this one, okay? Just consider this one. Consider this one. So what is inflow? Inflow, outflow, right? In is FA1, out FA2. Generation RA2 times V2. Just compare these two, okay? Compare these two. So what's next? Previously, I replaced FA1 using conversion, right? So now, I want to replace FA1, FA2 using the formula for conversion. So just copy this one. FA, let me write down the same formula twice. This one is from slide 9. From slide 9, the same formula, right? The same formula, but here, you put a 1 and put a 2, okay? Any number you can put. That is the information after reactor I. So the definition for X is very important, right? You can see this term, X2 times the inflow. The molar flow rate to the first reactor, because the definition is versus the feed to first reactor, so we can use this term. Any problem? Any problem? Okay, so bring these two into this equation. the same process can be applied on reactor 3, reactor 4, or reactor 5, depending on how many reactors used in the series system. So if you just do the same thing, you may know the volume for reactor 3 is like minus RA3, X3, X2. Okay? You can just copy, do the same thing. Because the right process is the same. If you change the form for this one, if you write down like this, you can write down like this, right? If you want to have the same form as rows, you can have this one. And because x0 is equal to 0, so this one is the same as this one. You can use the same form to express the volume of the reactor in series. If you finish this one, you can go to example 225. Slide 29. Let's see one example. Comparing volumes for CSTR in series. So remember the purpose in this class. One of the main purposes in this class is to find the volume of a reactor, right? Find the volume, to decide the volume. So maybe you want to convert, you want to have a conversion like 0.8 or something. You have a target. So what is the reactor you should decide to achieve this goal? So now we are still, there is still the same table, right? For example, 225, slide 29, you see the same table again. So we want to use the same data, same condition to analyze the volume. So previously we have used one CSTR or we have used one PFR, and we find the volume for PFR is smaller than CSTR, right? So if the reactor volume is important for you, if your space is not very large, your money is not very much. In that situation, you want to have a smaller reactor. So after calculation, you decide to use PFR. Okay, so now let's see the CSTR in series. If we have two CSTR in series, how to design? Use the same condition, and the target is also conversion equal to 0.8. Okay, we have to do this for two times. You can compare this example to previous two. Two CSTR connected in series. Okay, for the two CSTR in series, there is a typo. 改一下错字 ，OK? For the two CSTR I think in your problem that is I, right? I series. This one should be modified in series, okay? 2 CSTRs in series. 40% conversion is achieved in the first reactor, so 40%. X1 is equal to 0.4. Okay, what is the volume for each of the 2 reactors? The volume for these 2 reactors to achieve 80%. So that means X2 is equal to 0.8. Okay, so I have put all the information. You may write down some information by yourself if it is better for you. The reaction rate, the volume of reactor, you can have some definition. Also, the condition is the same as the previous, so let me show you FA0. Well, this one may be not very important, maybe not necessary. This is second, sorry, more per second. But it is not necessary to use this one, I just mentioned. So how to find the value? Can I directly use the formula? Okay, let me use the formula. So first one, V1 is equal to FA0 over minus RA, X1, right? Actually, you can memorize this one using the figure. If you remember, we have drawn the same figure for many times, right? Conversion versus this one. Remember, right? And we shade the area for volume. You can compare this one and this one. Or maybe this shape is easier to understand. What is the area? What is the area for this this shadow? This one? The width and the length, right? So you use this one times this one, you get the area. The area is volume. So you can use this figure to memorize this thing. But I still hope you can know how to derive. You have to know the process from the more balanced equation, but you can also directly memorize this term by using this one. Okay. So what is this one? You can tell yourself. Okay, you have to find this value at a conversion equal to 0.4 because after the first reactor, you got a conversion equal to 0.4. From the table, can you find it? 0.4, the value is 2.05, right? Please find it from the table. How about the conversion? Conversion is 0.4. Okay, so very easy. You got a volume for first reactor. Very easy. V2 is also easy. You can consider, you can memorize this equation also by using the plot. So the first term, FA0 over minus RA2. After reactor 2, you got a conversion equal to 0.8. Okay, How about this one? X2 minus X1. So use this one. You got this from table, right? From table at a conversion equal to 0.8. This value is 8. 8.0. Let me put a full number here. How about X2, 0.8, X1, 0.4. So we got a volume for 2 reactors. What's next? What can tell from this example? If you compare this example to previous two, what is the new thing you can find? So let's calculate the total volume for V1 and V2, reactor 1 and reactor 2. If you compare this one with single CSTR, do you remember what's the value? Previous example, if you use a single CSTR, use the same condition to achieve 0.8, 80% conversion. If you want to do this, but you only use one CSTR, you have to use this volume. But if you separate into 2 reactors, V1 and V2, the total volume, I think it is much smaller than the single one. So the conclusion is, if you use a series connection, you can reduce the total volume. But what's the cost? You have to prepare 2, right? You have to prepare 2 reactors. Even if the total volume is smaller, but you still have to prepare 2 reactors other than one single reactor. So last, how to tell the volume from figure. Figure is very important for this case. So how to tell the volume? Y-axis, FA 0 over minus RA. The unit is cubic meter. For x-axis is conversion x. Remember the original point 0. So if the curve is like this, we have solved this. We have done this many times, right? Okay. If the conversion, let me put a conversion. Conversion 0.8 and 0.4, right? 0.4 and 0.8. Okay, so what is the volume for V1, for reactor 1? Reactor 1, it is equal to this one, okay? Equal to this one. So V1 is equal to the Y is equal to X 0.4, right? When conversion is equal to 0.4, conversion equal to 0.4, you got this one, right? You got this one. What is this one? This point. This point means this one, right? This point. The value at conversion equal to 0.4. So, can you understand this one? This one. the area for this one is V1, right? The height is equal to this one. The width is equal to this one, right? So you use the area for this rectangle, you got a V1. How about V2? What is the Y? Y for V2? So here. This value is also FA0 over minus RA, x equal to 0.8, right? So this one, let me use white. So the area for this rectangle, this one, sorry. For this one, okay, the area for this one, the height is this value, right? The height. How about the width? x2 minus x1, okay? So the red one, the area for the red one is V1. The area for the white one is V2. How about the volume for single CSTR? Do you remember? For the single CSTR, the volume is the orange one, right? The orange, maybe like this, the orange one. So the difference between two in series and the single one, where is the area? Here, right? The area shown here. The blue one is the difference between this one and this one. So the blue one, this area should be this one, right? Okay? Any question? Okay, if not, let's go to slide 31. 31 is to compare PFR and CSTR. You can approximating PFR by a large number of CSTR in series. You can do this. So now let me draw a tubular reactor, PFR. So if the PFR is like this, this is the inflow. Okay, this is a PFR, right? But I want to approximate a PFR by large number of CSTR in series. So first, let me divide this PFR into several pieces. Let me have 5. Now, you can have many pieces, right? So let me just separate it into 5 pieces. 5 pieces. And then if you turn this reactor like this way, you got a five reactors. Okay, as you know, in the PFR, inflow goes to the first reactor, then goes to second one, third one, fourth one, and the fifth one, right? Continue. So that is like you have FA0 into the first one. Then this flow continue to enter the second one, third one, fourth one, and the fifth one, and go out. Right? So we can model a PFR with CSTR in series. We can do this. So the more CSTR in series, the behavior is more like a PFR. So the total size will be smaller when you connect more CSTR in series. How about another perspective? You can go to 32, slide 32. Okay. Wait for a minute. Next, I will draw a figure. As the figure you have seen for many times. Then we can have the area for the volume. So this figure is for conversion X versus FA0 over minus RA. Okay. The very familiar figure for you. So for the same data, we have the curve like this. Okay. If you divided the reactor into five CSTR connected in series, you may have, let me roughly draw this one. Okay. This one is X1, X2, X3, X4, and X5. Then the rectangle in the yellow color, the area is V1, V2, V3, V4, and V5. Can you find something? I mean, let me roughly draw this one. That means if you have several if you have several reactors connected in series like this, okay, several reactors, so many reactors connect in series, you can find the total area. The total area is much closer to the integral area, right? It becomes closer to the blue one. So like you can compare, if there are only two, okay. If there are only two, we got the X2 and the X5. So for the X5, from X2 to X5, you have, you have this area. From X2, you have this area, okay? So you can just compare. The yellow one, they are 5 reactors connect in series, so the total area is like this. If there are only 2, you see the red one, the first volume for the first reactor, for the second reactor, so you can find the difference, right? So if you use more reactors connect in series like this, the volume can be largely reduced. However, if you want to connect so many reactors in series, that is hard. Okay, so ideally, more reactors connect in series, you can use smaller volume. But in reality, to connect them, there are several points between them. There should be some problem at these points. So there is a balance between the number of reactors and also the total volume of reactors. So you should think about what is the balance and decide how many reactors connected in series is better for your system. Okay, let me stop here. So next time we will talk about PFR in series. Please also bring the chapter 3, okay? Next week.